Hello and welcome back to part 2 of the Delaware Tech Physics 111 Exam 1 Preparation and Practice Exam covering motion, also known as kinematics. In this section, we're going to discuss definitions of scalars versus vectors, and then we're going to give examples of each. The next page will cover 5 kinematic terms. These are various properties, and you'll see that 2 of them are scalars and 3 of them are vectors. So let's talk about the definitions. A scalar is a physical quantity described by a magnitude. A magnitude is basically a number value, a size, with a unit, if there is a unit. Not every property has a unit, but most of them do. So it's just the size of the number and the unit. And it has no directional component. There's no pointing in a direction saying it's pointing this way or it's over here. It's just an amount with a unit. And if you need to add up various numbers of different measurements within the same scalar, you just add them up. It's a simple addition. There are examples of scalars would be mass or time or distance, speed, energy, electric charge. Some of these things we'll get to in other units. But for instance, mass. Mass is typically measured in kilograms. And if I have a 20 kilogram mass and a 30 kilogram mass and I want to add them up, I just add up 20 kilograms and 30 kilograms to get 50 kilograms. Simple addition is good enough to calculate the sum of scalars. It's quite straightforward. Now, vectors behave a little differently. Vectors share a lot of qualities with scalars. They also are a magnitude, a number value with a unit. That number value could be little or small, just like a scalar can, but it also has a direction. It's pointing somewhere, up, down, left, right, north, south, whatever direction, over there, over here. And because it's associated with a direction, we often represent vectors by arrows. We'll show an arrow's direction, will tell you the direction of the vector, and the size of the arrow will tell you roughly how big the magnitude of that vector is. So we use little arrows and big arrows, and they're pointing in all these different directions to represent vectors. But when you add up vectors, you have to keep in mind the directions of these arrows, of these vectors. You can't just add vectors together. You can if they're in the same direction, but if they're in opposite directions, they end up being subtracted. And if they're in perpendicular directions, you have to use other kinds of math to add them up, often trigonometry, which is beyond the scope of this course. So we try to keep it fairly simple. Now, examples of vectors would be something called displacement. Displacement is like distance, but you keep track of which direction the movement to cover a certain distance is. Velocity is another vector. It's like speed, but it keeps track of the direction. So a speed might be 50 miles per hour, but a velocity would be 50 miles per hour due north or to the right or in the positive direction. Acceleration, which we'll talk about, this is the change in velocity over time. That's another vector. And then when we get into later units, we'll talk about forces, and all forces are considered vectors. Electric field is considered a vector. There are many different vectors in physics and in sciences in general. Okay, so let's look at some of these. So the first two I want you to consider are distance and displacement. Now, distance is a scalar and displacement is a vector. Distance we usually abbreviate with a lowercase d, and distance is just how far the object has moved, how much distance it's covered, how much it's actually traveled. So you can think of it as the number on your odometer of your car. If you go to the store and it's 2 miles away and then you come home, you've traveled a total of 4 miles of distance. Now in this course, we're going to try to mostly keep it to the metric system. So you can say 4 kilometers if we're measuring in kilometers, or it could be meters if it's a small distance. It could be centimeters if it's an even smaller distance. but we'll usually use some form of the metric system, some version of meters. Displacement, unlike distance, has to keep track of direction. So displacement is not how far you've traveled, it's how far you've gotten. It's how much you've changed your position from where you started. And we usually represent displacement with the term delta x if we're talking about horizontal movement. Later on, we'll be doing some vertical movement, and when we're talking about vertical movement, we use delta y. But for now, we'll use delta x. And anytime you see a delta, that symbol means delta something is always the final version of that something minus the initial version of that something. So delta x is x final minus x initial. Another way to say that is displacement, your change in position, is your final position minus your initial position. So you can imagine if you start at position we'll call 0, and you end up at a new position plus 5 meters. Plus 5 meters is your final position. 0 is your initial position. Plus 5 meters minus 0 meters is plus 5 meters. So your displacement would be plus 5 meters in that case. And you'll notice our unit is meters with some direction. And usually the direction is going to be plus or minus. We'll use that for direction. But in theory, you could use north-south, up-down, this way, that way. It doesn't matter. It's really going to be dependent on the problem. But any calculation we have you do, it's almost always going to be plus direction or minus direction. So anytime you have a vector, your unit should include a plus or minus unless it's 0. Continuing with this thought, we have two other terms, speed and velocity. Now, speed is a term that's based on distance, whereas velocity is a term based on displacement. Speed is distance divided by time. In other words, how much did you travel? How many meters did you cover over a period of time divided by how much time that took? That's your speed. And we use the lowercase v to abbreviate both speed and velocity. And I know that gets confusing, but that's typically what you use. You can always spell out the word speed if you prefer. There's no problem with that. So speed is distance divided by time, and we can always rearrange that equation to be distance equals speed times time. Now, if you're doing kinematic equations, which we do later in this practice exam, you will find that when the acceleration is 0, this simple formula is the easiest one to use, and all those fancy equations later on in this unit will just collapse to this very simplified equation. V equals d divided by t, or d equals v times t. And it simplifies everything if you know the acceleration is 0. How do you know the acceleration is 0? We'll tell you, hey, the rate is not changing, or the velocity is constant, or the speed is the same and it's in the same direction. That tells you there is no acceleration, and you can use this simple equation. And speed, since it's based on distance, a scalar, it is also a scalar quantity. We just use units of meters per second. We might use kilometers per second. We might use kilometers per year if it's a very slow speed. Okay. Velocity, however, is based on displacement. It's not how far a distance you traveled, it's how far you've actually gotten. What's your change in position divided by how much time it took. And how much time it took is properly referred to as the change in time. So we say that velocity is equal to the change in position, also called displacement, those are the same thing, divided by the change in time. Well, delta x, that's the change in position or displacement, is equal to x sub f, the final position, minus x sub I, the initial position. So it's the final position minus the initial position, and that's all divided by the change in time. Well, the change in time is the final time minus the initial time. And it's always easy to know what's the final time and the initial time. The final time is the larger and later time period. So if somebody says 12 seconds and 14 seconds, 14 seconds is later than 12, so 14 is your final time. And because velocity is based on displacement and time, displacement is a vector, so velocity is a vector. And velocity, like displacement, has to take consideration the direction. And now, because you've divided displacement by time, our units are meters divided by seconds with a direction. So we would say plus or minus meters per second is the unit for velocity, as opposed to just simply meters per second for speed. And the last unit I'd like to discuss is acceleration. Velocity is change in position over change in time. That's velocity. And once you have velocity, that might change too. So a change in velocity over change in time is how we mathematically define acceleration. Well, velocity includes both speed and direction, so acceleration really is any change in velocity over time, which means any change in either speed or direction over time. Well, for this particular unit, we're not going to worry about changes in speed so much, though you need to know that, but mathematically, we're just going to have you calculate things where you're changing the velocity in terms of how fast the velocity is, the speed of the velocity. So acceleration is defined as the change in velocity over the change in time. That's delta V over delta T. And as always, anytime you see a delta, it is always the final version minus the initial version. So delta V over delta T is V final, that's the final velocity, minus V initial, that's the initial velocity, divided by final time minus initial time. So it's a very similar formula to velocity, but you're using velocities to calculate acceleration, whereas before you use positions to calculate velocity. And acceleration is based on changes in velocity, a vector. So acceleration is also a vector. It also includes direction. And because mathematically you've taken changes in velocity, which have units of plus or minus meters per second, and now you're dividing it by another set of changes in time, you're dividing it by another second. The units are meters per second with a direction, and we usually just say that as meters per second squared with a direction, and the way we write that typically is plus or minus meters per second squared. And let's stop here.